Hello, and welcome back to the channel. Today we're going to talk about solving logarithmic equations. The objective for today's video is to use the definition of logarithms and exponential form to solve various equations involving logarithms. Now, when it comes to solving logarithmic equations, we're going to rely on the basic definition of a logarithm. The logarithm base b of x equals y if and only if b to the y power equals x. Now, both of these equations are equivalent to each other, but they're considered to be in different forms. The equation on the left is in logarithmic form. The equation on the right is in exponential form. And we can convert between these two forms. And so for most of our equations, the process is going to be to convert a logarithmic equation to exponential form in order to solve. Let's take a look at our first example. And this is a very basic example. The log base 7 of x equals 3. To solve this equation, we can simply convert this equation to exponential form. The base of the logarithm will become the base of the exponent. The 3 on the other side becomes the power, and the argument x placed on the other side. So we see here that by converting it to exponential form, we've practically solved the equation. X equals 7 to the third power, which if we evaluate, gives us 343. Let's kick it up a notch. Here we have the natural log of 3t minus 4 equals 2. So as we did in the first example, we want to convert this to exponential form. The natural log has a base of e. It's the logarithm base e. So when we convert this to exponential form, this would be e raised to the second power equals the argument 3t minus 4. Once the equation is converted to exponential form, we then solve the resulting equation. So we solve this equation for t. We can add 4 to both sides. That gives us 3t equals e squared plus 4. Divide both sides by 3 to get the exact solution of t equals e squared plus 4 over 3. The solution that we have here is expressed in exact form. If we want to approximate it, we can very easily plug this into the calculator and round it to however many decimal places that we need. But the important thing here is looking at the process for solving this equation. All right, so now for the next couple of examples, we're going to get into some problems that are a little bit more challenging. In this equation, we have the log of 2z minus 5 minus the log of z minus 13 equals 1. Before we can convert this to exponential form, we need to first condense all the logarithms on the left side into one term. In order to do that, we're going to utilize the properties of logarithms. Namely, in this case, we're going to utilize the quotient property of logarithms. Log base b of m minus log base b of n equals the log base b of m divided by n. Applying this property to the left side of the equation, we get the logarithm of 2z minus 5 over z minus 13 equals 1. We can now convert this equation to exponential form. Recall that if we do not see a base with a logarithm, it's understood to be the common logarithm, which has a base of 10. Converting this to exponential form would then give us 10 to the first power equals the argument 2z minus 5 over z minus 13. And then from here, we just solve the resulting equation. We want to clear the fraction, so we can multiply both sides of the equation by z minus 13. The left side becomes 10z minus 130 equals 2z minus 5. Subtracting 2z from both sides yields 8z, and adding 130 to both sides will give us 125 on the right side. Then we just divide both sides by 8. So our solution here would be z equals 125 divided by 8. Our next equation is somewhat similar to the previous one, but there's a little twist in the end that we'll need to take into consideration. The equation log base 4 of x plus the log base 4 of x minus 15 equals 2. As we did in the previous example, we want to condense the logarithms to a single term. In this case, we're going to apply the product property for logarithms. since we have a sum of logarithms in this expression. Doing so, this would give us the log base 4 of x times x minus 15 equals 2. Now having this condensed into one logarithmic term on the left side, we'll convert this to exponential form. So we have 4 raised to the second power equals our argument x times x minus 15. Now note in this case, we end up with what appears to be a quadratic equation. Cleaning this up a little bit, we have 16 equals x squared minus 15x. This is indeed a quadratic equation. Move all the terms over to one side. We'll subtract 16 from both sides, which gives us 0 equals x squared minus 15x minus 16. This quadratic expression is factorable. It factors as x minus 16 times x plus 1. Once we factor it, we set each factor equal to 0. That gives us x minus 16 equals 0 and x plus 1 equals 0. Solving each of these equations, we have x equals 16 and x equals negative 1. Upon inspection here, we find that we do run into a bit of a snag. And in particular, it's with the solution of x equals negative 1. If we were to plug that solution into the original equation, this would give us the log base 4 of negative 1. We don't even have to go any further. This is an issue because the logarithm of a negative number is not real. It's not within the domain of the logarithmic function. Since this particular solution forces us to take the log of a number that's outside of the domain of the logarithmic functions, this is what's going to be what we call an extraneous solution. Now, all that basically means is that it's a solution that we come up with when we go about the process of solving the equation, but it just doesn't work because there is a violation in the domain. So the solution of x equals negative 1, we would throw out. If we inspect the solution of x equals 16, we will find that that would actually be just fine because plugging that into the equation would not give us an error. It wouldn't give us a domain error. It doesn't give us an instance where we're taking the logarithm of a negative number. Therefore, for this equation, the only solution to this equation would be x equals 16. But what this brings to light is that with these logarithmic equations, we do need to check for extraneous solutions. When we check for extraneous solutions, we're looking at which of the solutions would force us to take the logarithm of 0 or a negative number. In other words, taking a logarithm of a number that's not in the domain of the logarithmic function. So we're going to finish up this video with a challenge problem involving logarithms. In this equation, we have one where we have the log of different bases. Here's log base 5 of x plus the log base 25 of x equals 3. We still want to try to condense this into a single logarithm. None of the logarithmic properties that we have account for different bases. The secret here is going to be to try to express both of the terms or all of the terms in terms of the same base. We can do that by applying the change of base formula. Log base b of m equals the log base a of m divided by the log base a of b. We're going to choose 5 as the common logarithm here. Now, in so doing, there's no reason for us to change the first term because it's already expressed in terms of log base 5. The second term, however, we will use the change of base formula here. This gives us the log base 5 of x over the log base 5 of 25. Note that in the denominator, the log base 5 of 25, we can evaluate that. Since 25 is 5 raised to the second power, that makes our equation the log base 5 of x plus the log base 5 of x over 2 equals 3. Log base 5 of x over 2 is nothing more than just 1/2 times the log base 5 of x. Now we can go about the process of condensing this into a single logarithmic term. First, however, we need to deal with the coefficient of 1/2. We can use the power rule to bring that coefficient up and make it a power of x to get the log base 5 of x plus the log base 5 of x to the 1/2 power equals 3. And now use the product property to condense the terms. This gives us the equation log base 5 of x times x to the 1/2 power equals 3. Now we can convert this equation to exponential form. The exponential form would be 5 to the 3rd power equals x times x to the 1/2 power. Then we simplify the right side of the equation and the left side. 5 to the 3rd power is 125. The right side, x times x to the 1/2 power, is x to the 3/2 power. And to solve this equation, we can simply raise both sides to the 2/3 power. On the right side, we get x. On the left side, 125 to the 2/3 power. In radical form, that's just the cube root of 125 raised to the 2nd power. We can take the cube root of 125, which is equal to 5, and then take that result, we square it to get x equals 25. So for this type of problem, if we have different bases, we want to express all the terms as a common base, and then using the standard properties of logarithms as we did in previous problems to solve the equation. Thank you very much for watching the video. I appreciate you taking the time to check it out. If you have any questions or any comments, or you want me to go over any topics, please feel free to leave a comment. If it was valuable to you, also consider liking and subscribing to the channel. Thank you very much.